So let's go ahead and start with shield volcano. Shield volcanoes we recognize because they have these gradually sloping sides, which makes them very, very what? Wide, thanks. So just at a glance, if I were to give you a picture, you could tell you're looking at a shield volcano just based on the width and the slope going up the sides. Okay? Do you guys know why they're so wide? It all goes back to the type of magma it has. So, I need red. Where'd my red one go? Red for magma. So the type of magma inside a shield volcano is always basaltic. And what's the one thing we just wrote down about basaltic magma? It is, the other one, it is runny. Okay. So I want you to watch what happens when I have runny magma and it comes out of my volcano. You know what it does? It oozes down the slopes. It's so runny it just spreads out for a really, really wide area. Since it has runny magma, it creates a wide volcano with gently sloping sides. Now, something else you need to recognize is when you have runny magma, it does not trap gas very effectively. So I just want you to visualize this for a second. Imagine you had a glass of water in front of you and a glass of honey. And you took a straw and you blew a bubble in the glass of water. What's that bubble going to do? It's going to come right to the top and pop. Now put your same straw in the glass of honey and try and blow a bubble. You can probably blow one. Is it going to go whoop to the top and burst? No. It's going to maybe come up to the top and it might pop, but it's going to take a lot longer, right? Runny magma has very little trapped gas in it. Now this is going to be significant because if you want a volcano to erupt, it has to have lots of pressure. You know where that pressure comes from? Trapped gas. So if I have very little trapped gas, I also have very little pressure. And we're going to turn this into a math problem. Take runny magma, add in the fact that it doesn't trap much gas and it doesn't build up much pressure, and what's that equal? Calm eruptions. Now keep in mind, calm eruption just means it's still a volcanic eruption. Is it still dangerous? Yes, you have melted rock pouring out and streaming out and sometimes spraying out into the air. Still dangerous, but on the scale of volcanic eruptions, you get calm ones. Because it's runny magma, which doesn't trap much gas, which doesn't build up much pressure, so you get blah, 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 blah. Okay? A couple of side notes with shield volcanoes. Where could I find them? Location. You tend to find shield volcanoes at ocean hotspots and divergent boundaries. Why do you get shield volcanoes at those two places? Well, that's because that's the two places that have basaltic magma coming up. And as you read through and do your notes today, you'll see why basaltic magma happens in those places. Good example would be the island of Hawaii is a massive shield volcano. And you just get to see the tip of it that sticks up out of the ocean. Now, as far as volcanoes go, this is one extreme. We're going to look at cinder cones next, and that is the opposite extreme as far as volcanoes go. And it has more to do than just size, so let's see what we've got. I need red, I need blue, I need purple. All right. Okay, for starters, looking at the size of this guy, how does it look different from my shield volcano? It's definitely much. Okay, so he is definitely short, and he's definitely steep. Now, the reason he's short and steep is because of the type of magma. He does not have basaltic runny magma. This specific type of volcano always has the opposite. So what's the opposite of basaltic magma? Okay, what kind was it that's thick? Rhyolitic magma. How about that? I can spell rhyolitic no problem, but I have a hard time with shield. It's dumb. All right, rhyolitic magma. Rhyolitic magma, we already said, is very thick. Since it's thick, guess what? Look back over here. What am I going to write under rhyolitic magma? Instead of not much trapped gas, I'm going to have a lot of trapped gas. And if it traps a lot of gas, guess what? It builds up pressure. A lot of pressure, thanks. And if I add all that up, instead of a calm eruption, I'm going to get explosive eruptions. Feel free to add your own sound effects as it explodes. Pew, pew, pew. Okay, so you can see the two things I just added. I jumped back to shield volcano. When magma oozes out and flows down the side, shockingly, it's called a lava flow because the lava is flowing. This guy doesn't have lava flows. You know why? Because the magma is too thick. It won't ooze out and flow. It just goes and blows into pieces. So instead of lava flows, we have something called tephra, which are also called pyroclastic materials. That's your ash. That's your cinders, that's your volcanic blocks and your volcanic bombs, which are the huge ones that come flying out and explode. So that's what you get in a cinder cone, is a bunch of tephra, ash and cinders. So where do we typically get these guys? Location. Location for most cinder cones is in one of two places. One, continental hotspots. And two, at the base of big volcanoes. Doesn't matter whether it's a shield volcano or a composite. Scattered around the base, you often find little cinder cones popping up. For example, if you ever are fortunate enough to go to Hawaii, go to the Big Island, that is the tip of a volcano. Mauna Kea is one of the extinct vents. They have big observatories up on top of there. All around the slopes, as you drive past it, these little cinder cones they're all over the place. You can't miss them. But that's all on the base of a big volcano. Go.
Could there be like a cinder cone volcano at the base of a cinder cone volcano?
No, but they sometimes happen in clusters. Like this is a big mountain made of solid rock. This is a pile of cinders. You couldn't build something on it if you wanted to. You could have one grow right next to it, and they kind of merge into each other. But you could have a little cinder cone on the side of it, like growing out the side. You couldn't physically have that because it's all just loose. You know what I'm saying? So they occur in clusters. You'll find groups of them together, but that's about all you can get. Okay, so here's our two extremes. Runny magma leads to calm eruptions and wide volcanoes. Thick magma leads to violent eruptions with lots of solid particles coming out. These are probably our worst volcanoes. Now, I know this is the thickest magma, right? So it should give us the most violent eruptions. But these volcanoes are small. They're so small, nobody's tempted to build near them or on them or next to them. And even when they erupt, they only affect an area right here. These guys are huge. For example, Mount St. Helens, Mount Hood, all the volcanoes out west, most of them are composite. That's because composite volcanoes are usually found at subduction boundaries. So most of our volcanoes on land happen to be this type. Since most volcanoes on land are this type, this is the type of volcano we're around most often. So guess which type kills the most people? These guys. And here's why. If this guy has basaltic runny magma, and he has thick rhyolitic magma, what do you think he would have? The medium one, right? Here's the problem. This guy could have, that's a question mark, any type of magma. Composite volcanoes can have runny magma. They can have thick magma. They can have the medium kind of magma, andesitic. But the problem is we just don't know. And they're not consistent. For example, Mount St. Helens, 1980, erupted with a fairly thick lava that mostly blew itself into pieces. Lots of ash. In 2008, 2009, it erupted again, same exact volcano. This time it was all runny basaltic magma. 2013, it erupted again, runny magma again. So what happens when it erupts next time? Is it going to be runny or thick or in between? Question mark. We don't know. They're not predictable. They don't follow any pattern. I know sometimes you'll read in a textbook or online that composite volcanoes are composed of layers of ash and then lava flow, and then ash and then lava flow, and they kind of imply that it erupts violently and then calmly, and then violently and calmly. That's not reality. Reality is they're unpredictable. They can go forever and not blow up, and then blow up multiple times in the span of a few years. Some of them are violent, some of them are calm. They might all be calm. They might all be violent. We can't predict that. There doesn't seem to be a rhyme nor reason to it. So, since it can have any type of magma, how much pressure builds up? It depends on the magma. What kind of eruption are you going to get? It depends on the type of magma. So, can I get lava flows? Yes. Can I get tephra flying out? Check. Yes, I can. Can I get both in the same eruption? Absolutely. If it's an in-between andesitic magma, you can have lava flowing down the sides while ash is spewing out all at the same time. So, composite volcanoes are unpredictable. We don't know what type of magma they're going to have at any given date. So as a result, we don't know what the eruption is going to be like. So, I could list some examples, but pretty much any subduction boundary. So Mount Fuji in Japan is on a subduction boundary. Most of them in the western United States, Mount St. Helens, Mount Hood, they're mostly composite volcanoes because they're on a subduction boundary. So anyway, in a nutshell, hopefully that ties together the type of magma with the features you see, with the type of volcano, and where you can find them. And we'll see if that helps.